There we go. I think now I've got the right microphone set up. So I seems like I've got a job later to find out which microphone it was turned to. Anyways, that is a problem for future me. So let's try this again. Oh hi. Um, Sorry, terribly distracted for a moment. So hello. Greetings, good evening, minions. I am, as always, Nathan. I am a PhD student in chemistry, and I am such an enormous nerd that I decided to take my free time and keep talking about chemistry because this just happens to be fun for me. And, and I tend to think that chemistry gets a bit of a bad rap. In that a lot of people find it difficult because it's often not explained that well. But quite aside from that, chemistry is hard. As it turns out, it is not easy stuff. I think it takes a long time to become comfortable with just doing chemistry, because I think nobody goes into it having any kind of intuition for what happens in chemistry. Like there's no parallel in kind of our everyday macro lives for the kind of things that we examine and that we learn about chemistry that happens on this micro level. It happens on a scale that we never interact with directly, and so there's no reason for us to ever have any kind of common sense about it. And so you learn a common sense that is often goes through the medium of math or pretty pictures, and that's how we get pretty kind of okay at doing chemistry. So it definitely takes a bit of a meandering path to actually understanding what the heck is going on. So, anyways, that's who I am. That's what I do. That's why I'm here. Yeah. So as always, this is a stream that is intended to just help people through chemistry to understand it a little bit better. And I am most familiar with teaching stuff at a university level, and so that's kind of what this is aimed at. But I'm always keen to talk about pretty much anything that's even vaguely chemistry related. Which, that being said, I'm always very willing to be distracted and go on go diving down some rabbit holes and just see where the conversation ends up. Yeah. So I've always got problem sets that I'll work through in the absence of any specific questions, but always feel free to ask me to focus on a particular topic, concept, what have you. I'm very willing to do that because this is supposed to be like sort of a tutoring experience. I'm very happy to talk about whatever people are interested in, and if that is at any time nothing in particular, I will just keep talking and like start going through some other chemistry problem sets that I've just accumulated over the years. Yeah. Oh, so I was just checking through some of my kind of just junk email. I get a lot of emails at my university account that I absolutely don't open. There's lots of different chemistry or science websites, vendors, but one of them is LinkedIn, because I have a LinkedIn profile that I have completely ignored for a lot of years, and I deliberately continue to do so because I just have neither time nor energy to engage with social media of any sort. Um, but it was really quite lovely because I saw from this random email that somebody had sent me a message on LinkedIn, and it was a name that I recognize because it's a student that I taught very close to the beginning of when I was starting to teach undergraduate labs. And this was a student that I very much enjoyed. She's a delight, a very nice person, and a keener, and I absolutely love that. My okay, not going to tangent right now. I'll spin off to a tangent later. But yeah, so as I went and looked at it, it was just this lovely little message that she sent, just to check in, see how things are going, and of course I reciprocated that, and so it's very nice to hear from her. And yeah, brought to mind a particular one of the highlights of my early teaching career. So at the end of each semester, I would invite my class to go to the pub on campus. I would do this like kind of after we're done all of the experimental work, and usually I try to make it after I was done marking, but not anyways. So effectively, at the time I took them out and bought them alcohol, I was not their teacher anymore directly. So I felt entirely okay about that. So yeah, I would always invite the class out, and say I would buy the first round of drinks or jug of whatever. So with this particular cohort that this student was from, who messaged me. We went to the pub as per usual, but we accidentally went on karaoke night, which I did not intend for this to happen, but but it was a really good night anyways. Not at all in spite of the karaoke night, but because it was karaoke night, we had a really fun time. And actually, this student who messaged me, she and I just decided to do a duet of A Whole New World from Aladdin, and it was spectacular because I can carry a tune if you give me a big enough bucket, but she was phenomenal, like absolutely spectacular singer. And so it went very well. Due not at all to me. So it was a great deal of fun. And then it's hard to say if that was a highlight of the night or if it was one of my other students. He was plastered, 3 sheets to the wind. This boy, and I supported him fully. And he went up and sang "Baby's Got Back," and boy had a good twerking game. What can I say? It was hysterically funny. But yes, anyways, very good time. We had a lot of fun. But yeah, so that's one thing that happened with my day. What was I going to rabbit trail about? Keeners. Yeah, like the people that get made fun of for being teachers' pets or sitting in the front row. They are absolutely the best. Because like, it's always very much appreciated as a teacher when the students are engaged and asking questions and just showing up and paying attention is kind of a big deal. And so when you get those students, it's always a good time when they make up at least a few students in the class. Because if nobody's engaged, it's not really a lot of fun. And I have had, well, I don't know if I've had actually any like entire classes where nobody was a keener. Usual class size is between 10 and 20. So usually there's at least one. Um, but yeah. Anyways, this is really neither here nor there. Um, but I guess all that just to say that as a teacher, I've got a very different viewpoint on keeners and teacher specs than I used to. They're the best, which is really nice to know because of course I used to be one. So that's a little bit validating. Alrighty. Okay. So I think what I'm going to do is I'm going to get working on some chemistry questions. So let's go to the board. All right. Okay. Yeah. So last day we were talking about. Well, last day we got off on a bit of a tangent because I had some questions. It's from a high school student who has shown up fairly regularly, and we were just talking about what orbitals are, because orbitals, of course, are kind of important in chemistry, as they are the things that do chemistry. But in terms of this problem set, so we're talking about different types of reactions and drawing out mechanisms for them. So last time we were working on this, we covered SN1 and SN2 reactions, and this one reaction actually does both of those. There's an SN1 reaction followed by an SN2 reaction, or vice versa. It can go in either direction, and this was the very meandering pathway that we took to answering that question. Yeah, so I'm not going to go over that in excessive detail. I am actually just going to move on to the second question here, which is about alkene addition reactions. And so this is generally where you use the electrons that are in a pi bond, so they're more loosely held to the nuclei. You use those as an electron source in order to go and do chemistry. And a very common way to do this is with halogens. There's certainly a lot of other reactions that make use of pi bonds as electron sources and or targets. One day I'm going to get around to talking about probably some Diels-Alder reactions, but that is not this day. So if we start out here, so look at what we've got. We've got an alcohol, we've got an ether group, and we've got a carboxylate group, so that drawn out fully would look like this. So that is what this functional group looks like all drawn out. Of course, there is also the sodium ion over here. That's just the counter ion for the carboxylate, just so we are charged neutral. So there's a couple ways that we can envision this reaction going, because if we've got a source of iodine, draw out all my lone pairs because I'm a good little chemist. So we've got iodine around, and iodine, being elemental iodine, I2, is actually a spectacular electrophile. And electrophile being something that wants to accept electrons in order to carry out a reaction. But the iodine is a good electrophile for two reasons. One is that the the bond here between the two atoms of iodine is entirely nonpolar. There's no electronegativity difference between these two, and as such, you could, if we were to map out the electron density, you could effectively cut that bond in half, and one electron from each bond would go to each iodine, and so they are charge neutral. Because the charge is always valency minus electrons, and when we're counting up formal charge for atoms, we count each bond by splitting it in half, giving one to each, which is, like I said, the situation that we're looking at here. So these are charge neutral. However, they effectively would have 7 electrons around them and not 8. So it is not a in this way of counting them, there is a deficiency of electrons. So it's effectively not an octet around the iodines, and so it is doable to add electrons into the system. And so when we do that, electrons coming from just some source, we're not going to specify which one yet, because it doesn't really matter, because any source of electrons that attacks an iodine is going to do it like this. So you attack one of them and form a bond to that iodine, and then, because that would be too many electrons, because when we're counting like this would be, if you formed another single bond to this iodine, there would effectively be 10 electrons around them, and that's too many. You can't really do that, and so this bond has to be kicked off and end up on the other iodine. So you end up with a neutral iodine over here and a negative iodide ion on the other side, and iodide carries a negative charge. However, it is important to remember that iodine is a very, very large atom. It is, I believe, in the 4th row. Fluorine, chlorine, bromine, iodine. 5th row. That's it. So yeah, it is a 5th row element. So this is very large. That means that negative charge is very diffuse. So it's quite stable, and that actually makes it a great leaving group for the other iodine. So the question then becomes, what are we going to use as a source of electrons? I don't know why I erased that entire thing, because I'm going to need to use it presently, but that is okay. Okay. So now we went over this as an alcohol, an ether, and the carboxylate. And so you may be tempted to use the negatively charged oxygen of the carboxylate as a nucleophile, because it's got all these electrons and a negative charge, and that generally makes things very good nucleophiles. But that's not what we're going to do in this case, because the carboxylate is not the best nucleophile here. It is not the best source of electrons to use, because there's a resonance structure in this carboxylate that acts by shuffling electrons from the negative oxygen to form a double bond, and then kicks this double bond up onto the other oxygen. So let's just draw the two. Okay, so effectively that trades the negative charge off onto the other oxygen, and this is an important resonance structure, because what this does is this fully spreads out this electron density. This negative charge is equally shared between these two oxygens, right? Because neither these structures as drawn are like equally good. And so this is essentially a 50-50 resonance structure between these two forms. And so if you have happened to catch my other discussions about resonance structures, it's important to remember what resonance structures actually are. These are not depicting two different forms that this molecule kind of oscillates between. So this is not, you take a picture of this molecule in one moment and it's got the negative charge up here, and the next picture that you take of it has the negative charge down here. That's not what this is at all. That's not what resonance structures are. So resonance structures depict two extremes of this. So how am I going to draw this? So let's say this one over here. Okay, so let's say that the two resonance structures that are drawn here are color-coded to the two ends of this spectrum. But the reality of what this molecule actually is something in the middle. So let's draw it instead like this. Okay, so that dashed line in between these two oxygens, that is this region of negative charge. So it's effectively a 1.5 bond between each oxygen and this carbon, because on the extreme ends you've got a single bond over here with a bond order of 1 and a double bond with a bond order of 2, whereas the reality of it is that each of these bonds is about 1.5 in bond order. And so the resonance structure in this case is right in the middle of these two extremes. And we can prove this crystallographically, because if you take the crystal structure of a carboxylate, what you'll see is, well, let's say, like, if it was this kind of exchange between these two extremes, what you would expect to see in a X-ray structure would be one of the carbon-oxygen bonds is long, which would be the single bond, and one of them is short, which would be the double bond. But that is not what we see in a crystal structure with a carboxylate. The carbon-oxygen bond lengths are exactly the same. Cheesiest of cakes. It is lovely to see you. Happy Friday. I hope you're doing well. How is the exam studying going? Do let me know. Yeah, so a resonance structure here is it's saying that both of these resonance structures exist simultaneously, and the actual reality of the molecule is the weighted average of the resonance structures, which is weighted by like how good, how stable, how optimal is that resonance structure in terms of minimizing charges and like everybody maintaining a full octet and all this such. Well, doing your trigonometry quiz as you watch. That's, oh boy. Oh man, me and trigonometry have a complicated relationship. We've decided to stay distant friends. My week's been going pretty okay. Just chipping away at work on my the paper that me and my prof are working on now, which is it's going to be a short paper, which I'm very happy about. It's the last paper I have to write as part of my PhD thesis, and hopefully it's going to be done fairly soon. What's it about? Oh boy. All right. Yep. It's time to go down rabbit trail. Okay. So, um, the paper that I'm working on now is it's an extension of what I of what my of what my last published work was about. Um, Geometry has always been a weak point for me compared to algebra. That's fair. Um, yeah, I like them both in principle, but yeah, they don't like me so much. Anyways, so yeah, basically what I did. So what I've done for like most of my work in my master's degree and now a lot of in my PhD was I made a bunch of uh, compounds called sulfur diamides. Like that. Yeah. And these go. Don't you worry about it. I'm not offended in the slightest that you haven't gotten to it yet. But yeah, so from University of Ottawa. Oh, cool. No, Ottawa's not me. I'm at the University of Lethbridge, over in Alberta. Um, but very cool. Yeah. When you do get a chance to read those papers, feel free to like bring them up and talk about them with me. I would be more than happy to just like read some papers and talk about it. Yeah. So sulfur diamides are these things. So the R just represents kind of whatever. Usually carbon-based is what people tend to refer to R as. But in the case of my specific compounds, made a bunch of these aryl systems. They really are. It's great. I made a whole bunch of these, and the X here was just a kind of variable group. I put different functional groups onto these sulfur diamides. I made a whole series of 9 of these things, and so I was looking at pretty much all of their a lot of their kind of important properties. Just like looking, like getting all the different like spectroscopic characterizations, just to build up a library of like, if somebody else is making this, then they can refer to my work and be like confirm that they've got what they think they've got. So I had crystal structures, I had NMR, IR, melting points, elemental. I did a battery of characterizations on these things. So that's what my one, like my really big paper was concerned with, was just documenting a bunch of the characteristics of these compounds, and with a big focus on their electrochemistry. And so what I was looking at there, so you dissolve them in a solvent, not water, because water tends to attack these things and break them up, which is not ideal when you're trying to examine them. So you dissolve it in a solvent and then run apply an electrical potential to these, so a voltage to the solution. And by doing that, you can measure like how difficult is it to force an extra electron onto this compound. And yeah, actually, very much like that. And so yeah, like this is like my paper is certainly, I think, the most extensive kind of library for the characterizations of this class of compounds. Yeah, so I'm pretty proud of that one. It's a good paper. It's really boring, but it's very good science, and I'm very proud of it. So this latest paper that I'm working on is I took these sulfur diamides that that I synthesized, and I tried to attach them to different metal centers. And turns out this is really hard to do. These things do not like to be attached to metal centers, and so we had to find some really like a really kind of not niche, but a very particular set of metals in order to just get them to stick on at all. And this has 4 chlorines on it. So yeah, it was a tin tetrachloride complexes that I made. Okay, I need to go back and read your question. How do you write out how difficult it is to add an electron? Like, is it primarily in words, or chemists do it primarily in numerical form? Certainly numerical form, because what this is. Actually, I can show you. Give me just one moment. I'll pull up the spectra that I collected in order to analyze that. Give me one moment. Graphs. Yes, this one. Okay. So. Yeah, when we're assessing how hard it is to put an extra electron into the system. Okay. Okay, so this is not a polished graph. This is just the Excel file of all these data points. But so this was for one of my compounds, and so. The x-axis here is the measure of voltage. So working with so what we use, we hook it up to this machine called a potentiometer, because voltage is a measure of electric potential. And using that, we apply a voltage to the solution, and then we change the voltage, and as we change the voltage, we're measuring the current between the 2 electrodes that are in the solution. Because when you start to when you get to a voltage where you force an electron onto the sulfur diimide, that produces a current, right? Because a current is just, essentially like a concerted movement of electrons, a flow of electrons. And that is what happens when you are, forcing an electron onto the sulfur diimide, is you're causing a flow of electrons in the system. So there is a responding current to that electrochemical process. And so we start the scan here, and we sweep to more and more negative potentials, and negative voltages are what force more electrons onto a system. And at more positive voltages, you see removal of electrons from the system. So when you get to a sufficiently negative voltage, then you start to see on the y-axis here, the y-axis is the current. And so you start to see the current getting bigger and bigger and bigger, and then it reaches this point here, this little saddle point, this minimum on the graph. And that minimum is kind of it's the nominal voltage at which this compound will be reduced, at which you have forced another electron onto the system. Does negative or positive / positive voltage remove / attract because of the same charges repelling? No. No, it doesn't. So negative and positive voltage does not refer to like a how shall I say this? It's not about like moving negative or positive charges, it's I might need to think about how I would describe that without getting mathy and gross and technical. Um, so let's just suffice it to say for now that that the more negative the potential, the more inclined the system is to force an electron, like to force an extra electron into the system that you're working in. Which say, like, if I've got a neutral sulfur diamide in solution, that's just sitting there. It's just sitting happy because it's like in this regime where nothing's happening. Then in order to force another electron onto that sulfur diamide, I need to have a more negative voltage applied. Whereas if I want to take that neutral sulfur diamide and remove an electron from it, then I need to have a more positive voltage. So like it's complicated. Like electrochemistry is it's pretty tough to just jump into, but it's like I guess it's important to avoid the pitfall of being like, oh, something with an electrochemical process at a very positive voltage is just like is going to have a positive charge or something like that. Like it's not that clear cut. Electrochemistry is a complicated thing because so I kind of explained why this change in voltage happens. I don't know why my mouse is just kind of like disappearing periodically. So as this current gets bigger and bigger, that is showing the process of forcing another electron onto the sulfur diamides. But then so this is the what's the word? I'm forgetting my basic terminology. Oh God. But like at this point, at the very edge of this trace, we reverse the change in voltage, and we start to sweep the voltage back towards a positive direction. And as we do that, you see this kind of curve in that current. So the current gets much more positive. And that is, so let's see. Okay, I'm going to put a couple text boxes here. So that's a very, very small one. Okay. Oh, that's great. Really, really nice. Okay. I can spell good. Okay, so in this area over here, this is where you find neutral SDIs, which is sulfur diamides, just the abbreviation for my compounds. Okay, and then at this point, SDI minus. So yeah, at this point in the graph, you've got this sulfur diamide with an extra electron, so it's got a negative charge on it. And then, so this process, well actually, yeah, the neutral SDI is correct back here. Because, so this process here that the current measures is the removal of that extra electron that we put onto the system here. And even that happens at minus 1.3 or so. So it starts from minus 0.5 and 0 roughly, then goes around counterclockwise. Yes, exactly. Yeah, so the trace starts off by going to the left. You see this, it's called a reduction process. That's the process of putting an extra electron onto the analyte, which is the thing that you're analyzing, or the sulfur diamide. So we go left, we put another electron into the sulfur diamide. We go back to the right now. We remove that extra electron. And then we get to this process. This is not a sulfur diamide. This is just the... this is another compound that we have in the solution. It's called ferrocene. And we just use it as a standard so that we know where this 0 point, like exactly where 0 is. Because we have to calibrate all of these electrochemical experiments. We have to know like where is 0 on the scale. And so we put in this compound called ferrocene that, you know, just kind of the chemistry community has decided, not arbitrarily, but they have all agreed that ferrocene will correspond to a voltage of 0. So that's what this graph looks like. Why does it start on the negative process instead of at 0? So that is because we in this particular solution, I have this ferrocene in solution right there. And so if I started with the potential at 0, there would have been electrochemical processes happening in solution as potential is applied. And that can have adverse effects on the rest of the spectrum. Weird things can start happening in the solution that are they're not simple. If you start at a point where you've got an electrochemical process happening. So we just started kind of in this area because nothing was really happening in that area, and because of that, so it's a nice quiet area, and that's where we started. Because this is one of many of these traces that I did when I was assessing this compound. So I would do probably about 60 to 70 different traces, and some of them I would start at 0. Some of them I would start positive, some of them I would start negative and go positive, and do all sorts of different experiments just to try and get a full picture of everything that's happening in the solution. Because like there's other traces like this one where we didn't. So like in this compound, or in this experiment, which is on the same compound, started close to the same place, about minus 0.4 volts. And we saw that first process, but we kept going. Instead of stopping the voltage here and sweeping back positive, we kept going to negative because there's a second electrochemical process that happens here as well. But yeah, so it's not for no reason that this one kept starting at this somewhat negative potential. Yeah, like this is another one where this one actually did start at 0, went through that first reduction process, and then went really far positive. But anyways, so I feel like that's not super helpful. Yeah, so this is the kind of graph that we get when we're doing electrochemistry, and so you'll see a lot of these in my sulfur diamide paper, and so like it's finding these kind of documenting these processes and finding these little minima and maxima that lets us start to build up kind of the electrochemical properties of all of these individual compounds. Yeah. So yeah, that was a spectrum of just the sulfur diamide, no metal complex or anything. But yeah, so I was talking about the paper that I'm working on now with my prof. Is we took the sulfur diamides and we got several of them to coordinate to this metal center. This one is tin, and yeah. So we got. These were really difficult to work with though, because these the silver diamides would coordinate very weakly to the tin. So a lot of our spectroscopic methods either didn't work or were done in such a way that this was not the only compound. Like sometimes you get like the sulfur diamide to tin complex plus sulfur diamide plus the tin and like molecules of solvent would come in and replace my sulfur diamide. So it's just it turns into a bit of a mess. Is what this does. Like there's a lot of good there's a lot of good characterizations we were able to do on this, and we know for certain that we made this stuff because I got X-ray crystallography of them. But yeah, the amount of stuff the amount of ways we were able to characterize these compounds was limited, for a lot of reasons that are complex, and almost certainly will be when we publish this paper, it'll be open access, so you can go get that one as well and read about it. And if not, I'm always happy to send people PDFs because knowledge should be free and it shouldn't be behind stupid paywalls. I very strongly object to this making science into a commodity. Yeah, thanks. No, I'm lucky. My professor is very much of the same mind. That as much as possible, we publish open access. Because yeah, depriving society of knowledge, or making knowledge less accessible, for the sake of profit. Of these publishing companies, not even of the scientists themselves. Scientists don't make money off of their publications. It is the publishing companies that make money, and it's offensive to me. I don't really. It's really diabolical how science has been commodified, and at the same time, the publishing companies very kindly request free labor from professors across the world when they do peer review. So scientists peer review new articles for free most of the time. Like very few of them get paid anything. Mostly just the editors. And so yeah, like there's just I could rant on this for so long. But yeah, like the while the system of peer review is essential, very important, and works well, it only works well because professors and people who are committed to science are willing to volunteer their time and expertise in order to review papers. Yeah, absolutely without pay, and it's which is completely insane to me. So yeah, like the scientists that do the work and publish these papers do not make money off of them. The scientists that review these papers and critique them and make them better or reject bad science, they do not make any money either. You'd love to learn about these issues because you recently got into some issues within your state about academic exploitation. I am so here for it. No, I am fully ready to get up on a soapbox and talk about it. Yeah, no, very 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 fair. But it's great that there's that you've got some interest in this, before even getting to post-secondary education. Because like it's really hard to know how to learn about how this stuff works. It's really only quite recently that I've been a big part of this publishing process, because it's like my papers that are being published now, and yeah, so this is kind of like a lot of osmosis over the years of learning little bits and pieces, but now like learning much more about it because I'm doing it. But yeah, no, it's a crazy system, and I so random is the issues with academia partly why the whole Alan Sokal thing happened. The papers were sometimes published because of reputation. I'm not familiar with that name in particular, but very certainly that is a thing that happens. People who become very prominent in the scientific community will it certainly has happened that they have used that status to kind of grease the wheels of getting their stuff published, and that's not a good thing. I think these days most of the time the identity of the people submitting papers to be peer reviewed, their identities are kept secret from the reviewers to avoid exactly that problem. And so there is a blinding in this process. So the authors submitting the paper do not know who the reviewers are. They're just named like reviewer 1, reviewer 2, reviewer 3. And I believe that the authors' names are kept from the reviewers as well. So there's a double-blind process, which is that's good. That's how it should be done, because somebody's identity should have nothing to do with whether their science is of good quality, whether it is well supported. Certainly, it is complex though, because so one thing to understand is that when authors publish, like the submission to reviewers does not cost the authors anything, but when the paper is accepted for publication, then there is a hefty cost. The articles that are like behind paywalls are usually like a couple $1,000 to like paid to the publishing company to or paid to the journal to and just wait for it, we're not done, because these are the papers that the publishing company still makes money on by like subscriptions, like universities subscribing to these journals for access to all its articles. So that costs an exorbitant amount for universities to have licenses from these publishing companies to access all of their articles. Or individually, you can go to these websites and you'll pay $50 to have access for several days to this article. But like those articles are the ones that cost the authors thousands to publish. But if it is open access, which are freely provided to anybody who goes there can download that. But the publishing costs to the authors, that is much higher, tens of thousands of dollars, often like $15,000 and upwards. I think usually not more than 20 or 25. But it's incredibly expensive. It's a huge drain on research funds, because this comes out of research funds from the PIs, and there can be like grants from from the university departments to help pay for publishing costs. Sometimes there will be grants or contributions from publishing companies if they're willing to throw some crumbs at the authors. But most of it is just comes from the research funds of the professor, of the principal investigator, and it's completely insane. So yeah, the publishing companies make mad money off of these articles, which is just pardon my French, but it is batshit crazy. Um, and it is like all of this serves to serves as a barrier to knowledge, like a barrier between the general public and knowledge, and I this is antithetical to academic pursuits. I think it is hugely adversely affects the both society in general and academia. It is actively harmful to both groups. Some of the names of publishing companies. Oh boy, I got a few. So I'll put a few in chat. So there's Wiley. There's RSC, which is the Royal Society of Chemistry. Oh god, now that I'm trying to think of a list of these things, it's going to escape me. Elsevier. I'm probably mispronouncing that, but I don't care too much. Yeah, there's lots. Because things like Wiley will have like a lot of hundreds of scientific journals under its umbrella, and I think that's the one that we published with last time. But yeah, no worries, of course. Yeah, there's certainly there's lots more. You could for sure just Google scientific publishing companies, various things. Just head down that rabbit hole. But yeah, so it's like at the moment it's so just like monopolies, kind of, yeah. But here's where it gets more complicated. Excuse me. So obviously there's tons of problems with how scientific journals are administrated and how this all works. And I've just been ranting about some of my problems with it. But there's another really big problem in publishing scientific articles, which is that less reputable publishing companies will do something called predatory publishing, which is where they will publish anything you send them. Their costs are lower, but they're basically to use a little bit of hyperbole, but not much. Their entire peer review process is just a rubber stamp where they're like, yeah, sure, this got peer reviewed, we'll publish it. When it is bad science, and this is how science that uses really bad methods or very, very small sample sizes that do not give a proper picture. Sometimes that's how these things get published. And people have done, there are studies in good journals of groups that have just tested these predatory publishers, just sent them nonsense articles, and gotten it published. And they'll be like, look at the crap that these people are publishing. And this is why we need rigorous peer review. This is why we need reputable oversight of the peer review and publication process, because this puts through bad science and deceptive science that now people will Like perhaps there's like a news company with an agenda will go looking for scientific articles to support whatever viewpoint they have, and they can find this bad science done in these predatory journals, and find support for their wrong-headed points, even though it's bad science, but the general public can't tell the difference between that, because they it requires training to be able to look at this stuff and be like, oh wait, this science wasn't done well. Their conclusions are not supported by their evidence. It takes critical thinking, which is also a skill that is trained and rarely intrinsic. So it takes critical thinking, and it takes knowledge of the subject matter to be able to find this science done badly, and methods that are inappropriate or badly used in this. So yeah, it's really tough. Sometimes, because the system that we have is crap, because it costs a huge amount to the scientists who could otherwise use those funds to do more science. So it's extremely expensive, and keeps this knowledge away from the general public. But then there's these bad journals who will just publish anything you send them, and that is also bad science. And also falls into a trap that many journals are seen as positions of authority. Like, I would be lying if I said I wouldn't fall victim being biased towards believing most of them. Absolutely. You are very, very much not alone in that at all. Because let me tell you, even it's tough. Even when you are looking up chemistry articles as a chemist, you there's a certain amount that you have to be careful with what you're citing, and just at least try to verify that that what you're citing has been done well. But that's hard when your one paper has over 100 references to other papers. It's impossible to read all of those with a completely critical eye, because you'd spend years just on that. And so critically assessing every single article that you use is not super practical, which is usually why you look up multiple references, because if multiple papers are saying the same thing and giving the same data points for a particular compound, for example, then it genuinely does increase the likelihood that is correct information. But it's always a balancing act between verifying that you're using good articles, but with actually publishing science. Wonder if they had Wikipedia, but for peer reviewing, or if that would even work. That's a tough one. And it's as many problems as I have with this system, I don't have a lot of solutions. Most of my solutions are, if you're going to charge for publishing. I don't have a fundamental problem with charging some money for the publication process. Excuse me. But asking scientists to volunteer their time to peer review is insane. And so they need to at least be paid some kind of honorarium, or give them a discount on their next publication or something. I don't know. But there's what is very clear to me is that the system that we do have in place, while it does provide rigorous peer review, which is an extremely important service, it is not a fully sustainable model, and there must be change around this, because they earned a lot to even be able to review such dense content. Where they worked a lot to be able to. Yeah, absolutely. No, it takes years of training and decades of years of training and years of experience to even be able to competently provide a review of an article. To even be able to provide peer review, it takes a great deal of training and experience, for sure. And that they just do this for free. I mean, it's great. Like I would do it for free too, because I love science, and I just think it's an important thing to do. So I'd be willing to do it for free, but I'd be happier to be paid for it. Um, so it's a modestly broken system, um, but at the end of the day, it's a system that we have right now, and what we cannot do is simply tear down the system without having a replacement, because we can't have like downtime. Um, no worries at all. So, personal question: but how do you guys make money if you don't get royalties and such? Are you paid for the research funds? We are paid through the research funds. So the professors are obviously like paid by the university. They have a salary, but that is completely separate from the research funds that they use to run a lab, and so they will apply for grants. In Canada, it mostly comes from NSERC, which is the National Science and Engineering Research Council. So NSERC is the major government funding body for academic research in Canada, and so that's where like most research grants come from here. There's several. There's NSERC is for natural sciences. There's ones like SHIRK for social sciences, and there's another one for health sciences. But so like government funding agencies are a major source of the research funds. A lot of professors are able to get research grants from from industry, from like big companies. Like if they're doing like cancer research, they may get grants from pharmaceutical companies. So there's a lot of like private sector funding for research as well. I often do not like the strings that come with that kind of funding, whereas the government funding tends to be a little better about like not having strings attached to research. So professors get their research funding from there's a certain amount that comes from the university, separate from their salaries, of course. But yeah, there'll be like university grants, there'll be government grants, and there'll be industry grants. Do private businesses fund usually affect the data like lobbying? I would venture that usually no. There I there there's definitely bias that gets introduced, and certainly this can have an effect on the data that comes out. So like I'm not gonna say that doesn't happen, because for sure it does. I don't think it's a huge problem, but I don't love it. I don't know how strict the regulations on that are in Canada, but no, in the USA we've had issues, especially with FDA and orthodontics. Yeah, the US. Oh boy. That's. Oh, I promise I'm not going to get super political about this. But yeah, there's been a lot of issues because no, I'm not going to get super into it because I don't honestly know a ton about it because I haven't had cause to get super familiar with it because I'm not involved in U.S. funding. But yeah, there's definitely been a lot of private sector overreach into that sort of thing and influencing of outcomes. And this can also come back to journals that are willing to subvert the rigor of the peer review process in order to just get publications out that they'll be paid for. Um, so yeah, it's not at all a simple issue. But yeah, getting back to like research funds. So the research funds that professors get from government, from university, from private sector, those go to purchasing all the chemicals, all the supplies, equipment, and to paying graduate students, sometimes paying undergraduate students as well, depending on what programs are in place, or lab managers, and whoever else they have around. So yeah, the salaries of people who work in the lab are paid through those research funds usually. And yeah, all of the operations, renting instrument time for like the big communal instruments at an institution, like the U of L has like several big NMR machines, and these are hundreds of thousands to over $1 million for the instruments. So they're kind of collectively bought by the department and the research labs, and then they kind of like rent time on these instruments is usually the arrangement that it has. They pay a certain amount per year to get access to these instruments. So yeah, all of those things come from the research funds from professors, from however they've procured those. Certainly is. Certainly is. Yeah. No, and this is why, like, with what I want to do. So I want to get a teaching position where my entire job is to teach. That's all I want. I do not want to run a research lab. I have known enough people who run research labs to know that I don't want that. Because a huge part of their job is applying for research funds and writing papers, which I like doing the work that goes into papers. I don't like writing papers. It's not fun for me. Yeah, that's a huge portion of a professor's job, is just managing that stuff, and I have no interest in that. I just want to teach. That's all I want to do. Right. So I think I'm going to spend about another 15 or 20 minutes streaming, because I'm pretty tired. It's been a long week. But with the rest of the time, I could talk a little bit more with you about orbitals and switch back to that. Oh yeah, no doubt. Yeah, it's not easy. It takes it takes a lot of work, takes a lot of brain power. Oh yeah. But what can I say? I like it for whatever reason. Maybe I just am a glutton for punishment. But yeah. So going back to orbitals. So just recall that orbitals are kind of divided into these categories of S, which are spherical orbitals, p orbitals, which are kind of that little figure eight, and then like d orbitals, which are kind of two figure eights, just kind of perpendicular to each other, a big X of orbital density. And the energy of these orbitals goes from like s orbitals are lower energy than p orbitals, which are lower energy than d orbitals, if we're working in the same energy shell. So like goes 1s, then 2s, then 2p, then 3s, then 3p. And so I drew a little diagram up here to kind of illustrate a little bit of the, like, so here's the energy differences. Because remember, in the first energy shell, there's only s orbital. There's no 1p orbitals. They don't exist. So there's only 1s orbitals, and they're way down here. And then 2s orbitals which are the very next energy shell, are way the heck up here. And then the p orbitals are just a little bit higher. So almost, but reverse those arrows. Because remember, like we're always interested in like what's the lowest energy conformation, because everything in nature tries to get to the lowest energy conformation. So s orbitals are lower in energy than p orbitals, and p orbitals. If I extend this, the 3d orbitals are up here. So yeah, that's just kind of the order of energy of these different types of orbitals. And then like all the 3s orbitals are higher in energy than the 2p orbitals because they go to the next energy shell. And when I say shell, here's kind of what I'm talking about. So if we've got a nucleus here, and we've got, here's a 1s orbital, then here is a 2s orbital, and here is a 3s orbital. And so the major difference between these is the size of the orbitals, and they're layered like onions, or ogres if you like. So the 1s, the 1s orbital is much lower in energy because it's much closer to the nucleus, and so these are the lowest energy ones, and then the 2s are a sphere outside of the 1s sphere. So these are these layered spheres with little nodes between them where there's no electron density, so on and so forth. But just think of it, little nesting dolls. You know those little dolls you stick inside the slightly larger doll and cap it up? Yeah. That's how orbitals do, and that's what's meant by these energy shells, is just the layer that these electrons are in. And so if you've got electrons out in these higher energy shells, then electrons in the lower energy shells are called core electrons, because they're like all of chemistry pretty much, let's say 98% of chemistry is concerned with what happens in the valence shell. And the valence shell is just whatever the outermost shell of electrons is. And so I had something for that as well. So if we go, whoop, not that one, over here. Yeah, so I wrote out a bunch of these different orbitals. And I'll go over those in a minute. But just say, if you've only got electrons in the first energy shell, then that is your valence shell, because it's the outermost. But once you get to the second row, to things like lithium, now it has electrons in the 2s energy shell. And that means that the electrons in the 2s energy shell are the valence electrons. That is the outermost shell. And now the 1s electrons are the core electrons. So they're kind of buried beneath the electrons in the outer shells, which is why they don't interact with other things, because they're kept in the internal layers of this atom. And likewise, when you get down to sodium, so like we're going hydrogen to lithium to sodium here in the different rows of the periodic table. So if you go hydrogen to lithium to sodium, now sodium has its 1 and 2 electron energy shells are completely full, and it's got electrons in its third electron shell, so its valence shell is just this. So your valence shell is whatever whatever layer of your electrons are the outermost. So that's the 1s, the 2s, the 3s, and anything in the same energy level, 1, 2, or 3, is part of the same valence shell. What shell can I Callisto? Hi. Woo. Do you want to come here? Come. Callisto. Hey, come here. Come here. Come. Do you want to say hi? Yes. Say hello. Hey. Yeah. Close enough. Hi. You're so good. Okay. Yeah, she's so good. Okay. Yeah, and so where was I going with that? Okay, yeah, I think I was just wanting to deal with these for now. Yeah, so I drew out just like the first 2 rows of the periodic table, plus sodium, because why not? And so this is how we draw out their electron configurations. So I've got it done both ways. I've got it with that 1s1, 1s2 for hydrogen and helium, but I've also got them drawn in the little squares, which is a pretty convenient way to draw out the electron configurations. And so I've got that for each of these, each of the atoms: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. And there's a bit of nuance as to how we fill these up and why we do that. And so there's two main principles that come into play. There's the Aufbau rule, or the Aufbau principle. It's called a few different things, doesn't super matter. And that is that you fill the lowest energy orbitals first. Whoops, that's a really long T. And the second rule, and I'll go back and talk about this more later, I'm not just going to leave you hanging. The second big rule is the Pauli exclusion principle. Good enough. Okay. One day I'm going to get like an actual, like, I don't know, a tablet or a stylus or something that lets me just actually write this stuff out, because that will be neater and faster. But today is not that day. Okay, so the Pauli exclusion principle says that no 2 electrons can have the same. Really, it's the same set of quantum numbers. Remember those numbers that we went over before. But another way to say this is no 2. Whoops, I forgot a word in there. No 2, we'll just say electrons, can occupy. Let's try to spell that right, shall we? Be good. The same orbital and state. So remember that an orbital can have 2 electrons, but these electrons are always going to be a pair of one of them being spin up and one of them being spin down, like these ones. Always, always, always. You cannot have, for example, 2 spin up electrons in the same orbital. It cannot happen. And that is because of, yeah, so remember when we talked about quantum numbers, there's these are variables in the Schrodinger equations that kind of are the mathematical solutions to what orbitals are. And so you got the energy level, you got the orbital type, the sp or d, you got the orientation, which is like the p, x, p, y, and p, z, the p orbitals that are facing different directions on the axes. But then you've got the ms, which says like this electron is either spin up or spin down. And so if they were both spin up, they would both, for example, have this +1/2 value for ms. And that is what the Pauli exclusion principle deals with, is you cannot do that. No two electrons can have the same set of quantum numbers. So if there are two electrons in an orbital, they must always have one spin up and one spin down. And it can never be otherwise. Okay, so these are the two rules that, taken together, allow us to fill these orbitals in a certain order and for reasons. Why is the numeral 1/2 rather than like 1 or another number? So I can't give a satisfactory explanation to that because because I do not understand the quantum physics around it. But so there is good reason for saying it's called like spin 1/2, either +1/2 or -1/2. And so it is this intrinsic property of the electron or of the particle, because things like neutrons have a spin of 1, not 1/2, but just 1. And that lends certain properties to the neutron, and being spin 1/2 just like has these certain quantum properties for the electron that kind of determine the magnitude and kind of directionality of the electromagnetic fields that electrons cause, right? Because electrons are this particle. Well, it's got wave particle duality, of course, but electrons are this particle that moves and has a charge, and any moving charge creates an electric field and a magnetic field, and that it is spin 1/2 determines some of the properties of this magnetic field that it produces. And that is about as far as I feel comfortable explaining it, because because I don't think I understand it well enough to do much better than that. What's important is that electrons can basically like occupy one of these two states, this +1/2 or -1/2, because this is called their magnetic spin. And again, it's not referring to a physical spinning, but it's referring to properties that arise from this electron that act as if it was a spinning solid object. If that, I hope that helps clear it up a little bit. But yeah, I maybe one day I will understand this to a greater extent. But for now, that's about all I got. Like a simulation. I'm not sure how to answer that. I'm not sure in what context you're meaning it would be like a simulation. Like having COVID having COVID but not the symptoms. I'm not sure if that's leading down a path I want to follow, because I think those are going to be in pretty kind of divergent categories. So yeah. it that's kind of getting it. It's like, yeah, because the electrons don't physically spin, but they've got properties that kind of like would arise from like if you had just like a bar magnet, like just like a fridge magnet or something, and you spun it, then it would create a magnetic field, or an electromagnetic field, anyways. And electrons make magnetic fields that are kind of like that imitate this property of spinning, but they don't spin like that. They've just got these properties that kind of mimic that, which I suppose could tie into why you think like a simulation. So yeah, they kind of like simulate the like having these properties without actually having this physical spin property. So yeah, yeah, I think I've run out of ways to say that, but yeah, like it's just this weird thing that just kind of happens, and it's a property of the electrons. Yeah, so like the wave particle thing, yeah, kind of. Yeah, like it's got these properties, but they're kind of fuzzy, because quantum physics is really really weird. Yeah, so basically this these rules tell us that when we put electrons into orbitals around an atom, you're always going to put them into the lowest possible energy level, the lowest energy orbital rather, and you cannot ever have two electrons in the same orbital with the same spin, being like spin up or spin down, plus a half or minus half, doesn't matter. So they're always going to be paired spin up and spin down. Yeah, so like when I write something like this, like this hydrogen atom, it's got a 1s orbital with one electron in it. You could also draw hydrogen kind of like this, where this is 1s, this is 2s, you got the 2p, you got the 3s, 3p, and so on and so forth. You can draw all of these orbitals for hydrogen because those orbitals exist. They are empty, they do not have any electrons in them, but they exist. And so when we're building the electron configuration for hydrogen, we've got one electron to work with. And so because of the Aufbau rule, we're not going to put an electron here first, because the 2p orbital is not the lowest energy orbital. That is the 1s orbital. And so that is where the first electron must go. Because the ground state for an electron in a hydrogen atom is the 1s orbital. And these orbitals that are currently empty but exist are the excited states. And so like with all that stuff we were talking about before, like having ground states and excited states, these are the excited states that electron can occupy, depending on how much energy it absorbs. Yeah, so as we keep building up, so with helium, you have a second electron. So now if this is helium, now we've got two electrons. So again, we're not going to put the second electron in the 3s orbital, because that's not the lowest energy orbital available. So we're going to take that electron and we're going to put it in the 1s orbital. And because the first one that we put in was spin up, this one must be spin down, because they cannot occupy the same orbital and have the same spin. Alrighty. And so then once we get done with the first energy shell, now like the 1s shell is full. There's no such thing as a 1p orbital. They do not exist. So the next the next orbital is 2s, and so if we now have lithium, so we've got 3 electrons to work with. Now we start to fill up the second energy shell, and so we put it in the 2s orbital, just like this. And beryllium, you finish filling out that 2s orbital, because again the 2s orbital is still lower in energy than the 2p orbitals, and so we fill that one first. And boron, of course, now the s orbitals are full, so now we put an electron in the p orbital. But now here's where things get a little different. So when we get to carbon, so now we've got 6 electrons that we need to put into these orbitals. So the first 2 go into the 1s orbital. It's the lowest energy, always going to be the one that we fill up first. Done. The 2s orbital is also full, and and the 2s orbital is lower energy than the p orbital, so that one is filled up, and that has taken out 4 out of our 6 electrons. So now we've got 2 electrons to put into the 2 p orbitals, and so there's 2 things that we could do. So here's 2 sets of p orbitals that I'm going to move so it's not behind my face. So what I've done up here is I put the second electron into a different p orbital. So I guess this would be, I'm just going to start with X because that's the first one alphabetically. And this one is the py orbital. So this is kind of the other option of what you could do. But spoiler alert, this one is better. And this is always the way that the order that we're going to fill these up in. We fill each of these orbitals in with 1 electron before we start pairing up a second electron. And so the reason that we do that is the same principle that guides 98% of chemistry, because I keep on saying it, and I'm going to keep on saying it forever, that almost all of chemistry revolves around reducing as much as possible the electron-electron repulsion, of spreading out electron density as much as you can. And so in this situation, in p orbitals, when you've got 2 electrons, those electrons are more spread out if they are in different orbitals, if they're in a px and a py orbital, for example. Because if you think about it, so here's, gotta move my face again. So let's just say okay, so that's a shaded side. Always remember to shade your orbitals, because there's 2 different phases, and those are very important. So let's put, so these are the 2 electrons. So this is, whoops. So this is the situation in this one, where we've got 2 electrons in the same orbital. One of them spin up, one of them spin down. That's how they must be. But in this case, we've got electron and 1 here. And remember, these p orbitals are always at right angles to each other. So, oh crap, I put it behind my face again, sorry. There we go. One day I'll be a good streamer. Not today though. Okay, so in if they occupy two different p orbitals, those p orbitals do not overlap with each other. Right, because they're always at right angles to each other, or orthogonal to each other. I don't know what I'm doing with my fingers. Please ignore me. But yeah, so putting one electron in each of these orbitals spreads out the electron density more than putting them in the same orbital, right? Because when you put two electrons into the same space, they will experience electron-electron repulsion with each other, and that is greater, like, because so these electrons in these two different orbitals, of course, they also experience that electron-electron repulsion, but less of it because these electrons are further away from each other. So the double one is still a p orbital. Yep. This is px and py. So this is two p orbitals, and this is one p orbital. So d orbitals are something else entirely. We'll definitely get to those. Not today, but we will get there. So this is just two p orbitals, right? Because so it's important to remember that these orbitals always exist. So this one also has a py orbital, but in this case it's empty. So there's no electrons in this orbital, and there's two electrons in this one, whereas this picture has one electron in each orbital. And this serves just to keep the electrons further away from each other, so that you have less electron-electron repulsion. And that is what makes this a lower energy state than this, because it is like pairing electrons is a more energy intensive process, and we still do it, and like it has less of an energy cost to have, for example, two electrons in the 2s orbital than to start putting one of those electrons in a p orbital. Yeah, so this is always going to be the case when we're filling up orbitals. Is you fill each orbital with one electron before you start pairing electrons. So nature naturally pushes to spread the density, like it's constantly trying to achieve for the spread. Yes, yes, with caveats. So yes, in that we always want to spread out the electron density as much as we can. But remember that there are also attractive forces between the proton and the electron. So electrons want to be around protons because there's that attractive electrostatic force. But electrons don't want to be around other electrons. But when your nucleus contains tons of protons, it gathers a lot of electrons around it. But you still spread out those electrons as much as you can with the space that you have. Is that what the heat death thing of the universe is, or is that different? It's kind of similar, actually. Basically, the heat death of the universe is saying like one way to describe the heat death of the universe, of which there are many. Like this is just one way to describe what it is that at the heat death of the universe, everything, every atom, every molecule has reached its lowest energy state and then just stays there, because there's no extra energy around to motivate things to occupy higher energy states, because so basically here you go. Here's something you'll recognize. At the heat death of the universe, like there'll still be, like, if you want to do a chemical reaction, here's your activation barrier. But at heat death of the universe, everything's energy is down here, and there's nothing that can input the energy that's needed to get over that activation barrier. So nothing can react with anything else. And that is heat death. It's from a chemical perspective. Yeah. Yeah, it's like all of these things just are so interrelated with each other. It's absolutely delightful. Oh yeah, no, it's absolutely very fun to learn about. I think mostly because I will certainly never experience the death of the universe, which I'm happy enough for that. That wouldn't be great. Um, yeah. Um, okay. So one more thing that I want to um, say about these electron configurations, and then I am going to sign off because I'm a sleepy boy. Um, so there's also okay. Oh, I'm always willing to rabbit trail. Could it happen spontaneously, or is it always gradual? Um, like a heat death. I mean, I'm not sure how to answer this. So it that depends, I think, on your definition of spontaneous. Because I think I could argue that heat death is both spontaneous and gradual. I think it would be hard to define it as anything but gradual, because this is something that would take, I think, is something like quadrillions of years, like, if not more. I'm genuinely not sure. But it takes an exceedingly long time for heat death to happen, because there's a lot of energy in the universe, and so despite things happening spontaneously, and again, like there's the word spontaneous has some very specific meanings depending on what it is you're talking about. And I think I won't get into that now, but yeah, I think I could convincingly argue that heat death would be both spontaneous and very gradual. Um, oh, actually, I've got a good. Okay, so no, I've got a really good I've got a really good way to talk about that. Okay, spontaneous versus gradual. Uh, so, um, so spontaneous reactions are kind of defined as actually something exactly like this. And the key to like what is a spontaneous reaction is that the products of the reaction are lower in energy than the reactants, and so that's that by strict definition is all that's needed for a reaction to be spontaneous. Um, However, uh, the spontaneity of a reaction does not make any comment on the activation barrier to that process. Uh, so, an example of something that is uh, technically a spontaneous reaction, but we do not see it happen, is uh, diamond to graphite. So, diamond and graphite are both made up purely of carbon. They're like diamond. It's like carbon. Oh god, that's barely a C at all. What am I doing? Oh no. Nope. I want to get there. Okay. So diamond looks like this. It's carbon, 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 carbon. They're all connected by single bonds. And In a well-formed diamond, that's all there will be, is just carbon on carbon on carbon on carbon, for goes on forever, but all connected by these single bonds. And so, and remember, that means that just like in a model kit, it's a three-dimensional thing. So they'll all be connected like this. And but if you take, by contrast, graphite. So graphite is like pencil lead. It's that gray, like almost oily kind of thing that just like gets shaved off of pencil lead as you write stuff on paper. And that's what graphite is. And graphite is made of a whole bunch of interconnected how have I made my yeah, and then this would have to be double bonded to something else. Anyways, so graphite is made up of all of these interconnected rings of okay, I've made all these double bonds wonky. So let's just make all of them the circle of aromatic rings. So graphite is made up of all these rings. Graphite is also just carbon. Every one of these points is a carbon atom that's connected to another carbon atom. But they exist in kind of sheets of these interlocked rings that are flat. These rings are planar, so they're completely flat, and they basically exist in layers, kind of offset from each other. Like there will be like a there. This would be like two layers of graphite, kind of interlocked on each other. So the purple and the green are like two layers of graphite, and so these layers are not strongly bonded to each other, so they can kind of slip off of each other. Yes, exactly. Yeah, the layers are why graphite is weaker than diamond. Diamond doesn't have these kind of layers because it's just got this lattice. It's just called a crystal lattice of just all of these connected atoms that go out in 3 dimensions, and they're all kind of locked to each other. Whereas these graphite, these layers of graphite, there's no single bonds. There's no bonds between the layers of these rings. They're just sitting on top of each other, and there's some attraction to them by some more complicated processes that I don't feel like talking about. But essentially, they're not strongly bonded to each other, so they can slip away. So, the thing is, yes, diamond is stronger, but graphite is lower in energy than diamond. If you take a sample of graphite and a sample of diamond that they weigh the same, they've got the same number of carbon atoms, the graphite is in a lower energy state than the diamond. So this reaction here, going from diamond to graphite, is thermodynamically spontaneous because the products are lower in energy than the reactants. However, you could set a diamond on a desk and use it as a paperweight until the heat death of the universe, and they're not going to turn into graphite because this activation barrier is huge. So you do not see any you do not see a diamond just like slowly turning to graphite over time because it does not breach this activation barrier. It takes a lot of energy in order to get it up there. It's lower energy because it's more fragile or changeable in structure, like water to gas. No, I think. Yeah, exactly. Yeah, solids generally have a lower are in a lower energy state than a liquid or a gas. But they're stronger, they're more solid, they're more dense. Usually, except for water, which is a weirdo, and ice is actually less dense than water, but which is why life can exist. Yay! Um, but but yeah, generally solids are lower in energy than liquids and gases. Um, but yeah, like lower in energy doesn't mean weaker or fragile or anything like that. In fact, lower energy things tend to be denser, more solid, often stronger. Um, but not necessarily so, because there's a lot of factors that go into like, is this thing strong? Like, is this thing hard? Is it brittle? Is it flexible? All these different things. It's really complicated as to what the physical properties of something end up being. But in terms of just the simple energy of the system, something like graphite is lower in energy than diamond. Yeah. So yeah, in that way. So this I think this started out as me kind of describing spontaneous versus like actually happens. Because yeah, reactions that are spontaneous in the thermodynamic sense of products being lower energy than reactants. Those reactions are not, they don't necessarily just happen. So like we could, given enough energy, and like with specific reaction conditions, we could turn diamond into graphite. But it takes a crap load of energy, and I genuinely don't know if that's actually been done, but you know it could in theory be done. And if you were to do that, then you know the reaction itself, once it gets over that activation barrier, that would release a great deal of heat. Yeah. All right. I need to hydrate. Okay. Really quickly going to go over this last thing, unless there are more questions, which I'm always here for. I just, yeah, I will forever be distractible. But yeah, so there is a reason that I did not draw them like this. I'm going to need some more space. That will do. All right. So, when we are populating these orbitals, we put one electron in each orbital, that in each orbital that has the same energy, because these px, py, pz, they all have the same energy. They're called degenerate orbitals because they've got the same energy. So when we're filling these with one electron, we must fill them with the same. They must have the same spin in order to satisfy the Aufbau rule, where we fill the lowest energy orbitals first. Because this, with one being spin up and one being spin down, is higher in energy. Ooh, that's messy writing. There we go. And so so this just has to do with, right? It's so good. Yeah, it's just a little playlist called, I think it's Stream Save Stream Safe Gaming Bops, and I love it. Because yeah, none of this stuff is copyrighted, so I can play it freely, and it's delightful. It's really good. There's some weird ones, but mostly good. Yeah, so this just has to do with the interaction of the electromagnetic fields around the electrons. So if they are both of the same spin, if they have, that's to say, like the magnetic field that they produce has the same properties, then that is a lower energy state than the spins being opposed to each other. And again, that's about as far as I understand it. I do not know I do not know like the detailed explanation of why this is, but it is a lower energy and therefore more favorable situation to have the electrons with their spins aligned with each other rather than anti-aligned with each other. And of course, there's no preference for spin up versus spin down. Sorry, there's a little fruit fly. It was very distracting. So this spin state is equally favorable to when they were both spin up, and those are better than having them in different spin states. Yeah, so basically like following those two rules and just keeping in mind that the way to lower electron repulsion the most is to have the spins aligned. Then that is the entirety. Like that is sufficient to explain the entirety of how we fill up orbitals in the correct order, so that we're always getting the lowest energy configuration. All right, and if that doesn't fry your brain, it does mine. So I think that is where I'm going to call it tonight. Unless you have any final questions, always feel free. And yeah. All right, what are we going to do next time? So NPR 210. Hello, it's good to see you. Just stumbled on this channel. I've been appreciating the nostalgia from high school and uni. Well, thank you so much. I really appreciate that. Yeah, I'll be here every Tuesday and Friday if you want some more nostalgia. If you haven't been around for any of my introductory spiels, I'm a chemistry PhD student. I'm a few months away from done my PhD, and I am a big enough nerd that in my free time I come on here and I talk about more chemistry because I think this stuff is fun. So yeah, I really appreciate you coming by and saying hello. But yeah, I'll be here every Tuesday and Friday, just kind of plugging away at random little problem sets, and then just kind of talking more about whatever people are interested in. But with the sulfur diamides, I'm definitely fried. That is more than fair. I am also. So yes, I really appreciate you all coming out and having a good nerdy time with me. And I hope you all have a lovely weekend. Take good care of yourselves. Okay, bye.